Alright, so last time we left off with this definition. Given a metric space M and an element X in M, positive real number R, the open ball around X with radius R is denoted this way, B sub Rx, and it's the set of all Y in the metric space whose distance from X is strictly less than R. Not less than or equal to, strictly less than. Okay, and so for the metric space, that's just the real numbers. With this typical straight line metric, the open bool around X is the interval from X minus R to X plus R. And then for R cross R, with the Euclidean metric, the open ball around R is the disk of radius R around the central point, AB. With the taxicab metric, the ball of radius R around the point AB is this diamond. And with the max metric, the ball around AB of radius R is this square here. Right, so when you look at all three of those open balls together for those three different metrics in R cross R, they look like that. Right, so the taxicab metric one is the smallest of the bunch, then the Euclidean metric, and then the max metric. And then, very important concept in metric spaces is the concept of an open set. An open set is somehow a generalization of an open ball. Okay, how is it a generalization of an open ball? Well, as follows. Given a metric space M, a subset O is called open when for every X in O, there is an open ball around X that lives inside O. So, no matter where this element X is in this set O, you can always find an open ball around X, and it stays inside O. Very important concept. Example, the open ball itself, Brx, is itself a metric space. This will be a homework problem, so that's right here. That's number 3. So the open ball itself is a subset. So the Brx, the open ball Brx, is itself an open subset. Okay, that requires a proof. The picture to think about is this. So the picture to think about here so here's X, and here's the open ball around X. What do you need to show it's an open set? Given Y in Brx, so where's Y in this picture? Where's Y in this picture? Where's y in this picture? Is it right here? Is that y right there?
Can you hear me now?
Oh yeah, I can hear you. I'm sorry, you were trying to say something.
Oh, sorry, my mic was having issues. I was trying to answer the question.
Yeah.
I was
Where in
saying
BA?
somewhere in the circle.
Somewhere.
The larger
Should be
circle?
right here. Is x equal to y?
It could be,
Could be. Does it have to be?
but it's not necessarily.
No, absolutely not necessarily. So the ball of radius r around y, that'll be inside of brx, right? The ball of radius r around y, that'll be inside x, right? brx, sorry. No, it won't be. The ball of radius r around y will definitely not stay inside the ball of radius r around x, especially if y is like all the way out here. I mean, let's not put it out there. Okay, you need to find, so here's y. You need to find a radius, and you need to say what that radius is. Okay, so this is S. So given y in BRX, find S and say what S is, such that BSY is a subset of BRX. You can't just say, oh, okay, there is an S, and do it. You know, there has to be an S that works. You can't say that. You got to tell me what S is. Typically,
And I assume this S would have to work for any element y in the radius?
No. For that particular y, there is an N
Okay.
particular to this y, right? I mean, as you get, I mean, like, oh, if y is,
That's what I was thinking.
I mean, the S can be pretty big.
Edge,
Yeah, as you get closer to that, it's going to get really tiny. Exactly. Mm-hmm. Yep. So you have to say what S is, and typically that's going to be in terms of r and y somehow. So typically, S is expressed in terms of R. So you have to find an S, and then show that BS. So this is 1, and this is 2. Show that BSY is a subset of BRX. How does one do that? How does one show that one set is a subset of another? We still didn't quite get this on the exam. How does one show that one set is a subset of the other?
Sure that any element in the subset has to also be in the larger set.
How do you write that in English? So
given an element in B R Y
S Y. Yeah. What
B S Y.
Yeah. So take
Sorry.
X in B S Y, right? Can you use X?
I would assume no.
No.
It's already
X is already being used. You got to give it a new name, Z, or
like,
whatever. All right. Let Z be an element of BSY. Blah.
Go through the steps.
Blah.
Thus, Z is also an element of BRX.
Z is an element of BRX. Done. So in this picture I'm drawing, notice that the ball looks like a ball. It's round. Does it have to? Am I talking about R cross R with the Euclidean metric?
It would not have to be round. No. I have a question about S.
You have to have some intuition to work with. So in that case, one metric space is kind of as good as another for any, working with intuition. But, you will have to use in this proof the triangle inequality. Right? So the proof, it should be a little bit more detailed, actually. I don't know. Let me try to make this more detailed. So I'm giving you a template for this homework problem, so one should follow the template. So I give templates, and then I see people not using them. So it's not copyrighted. Of course, you actually have to be present in order to know that there is a template.
And here I thought I had a site too every time I used one of your templates.
What's it? Yeah, as long as you don't. No, I'm not going to say it. I'm not going to say. I'm going to resist.
I have a question about S.
Yeah, one second. Just let me write this stuff down because this is important.
Okay.
Okay, so one, given Y, find S. Typically S is expressed in terms of R. You can't just say S exists. One needs to say Y. So here, for this second part, show that BS. So do this as follows. Let Z be in BSY. Blah, blah, triangle inequality. Blah, blah, less than R. So, X is, or not X, it was Z. So Z is in BRX, period. So let Z be in BSY, blah, 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 triangle inequality, blah, 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 less than R. Therefore, Z is in BRX. That's the way the proof will look. Not with blah, blah. You have to fill in the blanks, of course.
I thought this was going to be a really easy test.
Yeah, just write that. Yeah, okay, no. You had a question about S?
Yeah, does S have to go to the edge of like touching
No,
R?
no. Any S.
Okay.
Once you find an S that works, anything smaller than that will still work.
Okay.
Yeah. Okay. All right. And then there was another problem about. Here it is. In the homework that I left there about open balls. Let number 2, let M be a metric space, and let X and Y be elements of M, X not equal to Y. Prove there are disjoint open balls, BRX and BSY inside of M. Okay, so you have to tell me what R is and tell me what S is, explicitly, what they are. Okay? And then you have to show their disjoint. Right? You have to tell me what R and S are explicitly, not like R is equal to a half or R is equal to 10 to the negative 10,000 or something like that. No, you can't say an actual number. You need to tell me what it is explicitly. It's going to be in terms of the distance from X to Y. Let me write that down. So for number 2, so this one that we just did was number 3. For number 2, so for problem number 2, so show that, so find R and S such that, BRX intersect BSY is empty. So you must state explicitly what R and S are in terms of dxy, the distance from x to y. Then actually prove that BRX intersect BSY is the empty set. Do that by contradiction. So do this by contradiction by assuming there is some z in BRX intersect BSY. So do that by contradiction by assuming there's something in the intersection of the two, and then showing that that's a problem. Again, triangle inequality will be used. Okay. All right. And then the last thing we did was this theorem: if O1, O2, O3. So if you got a bunch of open sets in a metric space M, then the union of those open sets is still open. So how do you show that? What's the definition of an open set? You need to take an element X in the set and find some ball of radius R around X that's still in the open set. Well, it's pretty easy to do. It's because OI is open. Okay, so let X be in the union. Therefore, X is in one of the OIs. And because OI is open, it satisfies the open set property, which is that there is some R such that BRX is a subset of OI. Therefore, BRX is a subset of OI, which is a subset of the union of all the O's, and you're done. Okay, think about the following problem. So let O and P be open subsets of metric space M. Show that O intersect P is open. So whereas the union of open sets is open, even infinitely many open sets, the union of infinitely many open sets is open. With intersection, no. It's just finite intersections will stay open. Infinite intersections won't. All right, some examples of non-open sets. So here's a non-open set. Right, like the interval, closed interval from 0 to 1 in metrics, right? So this is equal to the set of all x such that 1 or 0 is less than or equal to x is less than or equal to 1. Right, which is a subset of the metric space R, where the metric in R is, as usual, that the distance from x to y is just equal to the absolute value of x minus y. Now this set is not open. Why is it not open? Right, here's a 0, and here's the 1. Why is this interval, this closed interval, not open? Where does there not exist an open ball that stays inside that set? So for any positive r, also for any r bigger than 0, the ball of radius r around 1 is equal to, right, well, it's the set of all x such that 1 minus r is less than or equal to, or less than x is less than 1 plus r, right? But there's always a number bigger than 1 around that, right? So 1, or inside that is 1 minus r, 1 plus r, right? There's always going to be some number in BR1. There's always going to be some number there that's not in the interval from 0 to 1. Right? 1 plus r, that's a positive number. So between 1 plus r and 1, there's always something. Like what? What number would be like right here? What number is in here? That's bigger than 1 and less than 1 plus r.
1.2.
1.2. What if r is equal to 0.00000000000 what? That won't quite do it. You can never give an actual explicit number. It always has to be in terms of these distances that you're talking about. In this case, r. So what number would be there where that arrow is pointing? Right, and r can be really, really, really tiny. I mean, tiny, tiny, tiny. I mean, smaller than the Planck constant. But it's still positive. So what number is still positive but less than r? What number is positive but still less than r? If Zeno was around, he would tell you. But I know you guys all know Zeno's paradox.
Can you just say like half of r?
Yeah, exactly. Such as 1 plus r over 2. Right? It's still positive, so it's bigger than 1. But it's less than 1 plus r. Right? That's exactly the way you want to do it. All right, and then there's another example. So while the union of infinitely many open sets is still open, the same cannot be said said for not closed sets, intersections. So take the following open sets in R. The ball of radius 1 over n around 0, which is equal to the interval from minus 1 over n So 1 over n in R, which is equal to the set of all x, such that minus 1 over n is less than x is less than 1 over n inside the metric space R. Right, so on the number line it looks like this, right? Here's 0, here's like, right, minus 1 to 1, and then minus a half to a half, and then minus a third to a third, minus a fourth to a fourth, minus a fifth to a fifth, so on and so forth. All right, so like this right here is the open interval from minus 1/3 to positive 1/3. So now, right, the intersection, so B1, 0, intersection B1 half, 0, intersection B1/3, 0, so on and so forth, just keep going like that, infinitely long, is going to be equal to what? What's going to be in the intersection of all those sets? B1 half, 0, B1/3, 0, B1/4, 0, around 0, ball of radius 1/4 around 0, intersection the ball of radius 1/5 around 0, so on and so forth. What are you going to get when you take the intersection? Just 0 itself. By the way, this is 0, right? Yes? That's a 0.
Yeah, that looks like 0 to me.
That's a 0. What's this?
Nothing.
That's the empty set.
Yeah.
Not the same thing. Yeah. I know, like in you know, they do this in computer, ASCII sometimes, okay, but that's just a way of writing 0. The empty set is this. Different. Not the same thing. That's just 0, and this set is not open, right? And 0 is not an open set in R. Right, because for any positive R, the ball of radius R around 0, right, is the interval from minus R to R, which is not a subset of 0. You can't put an open ball around 0 and have it stay within the set 0. Right? So unions of infinitely many sets, infinitely many open sets is still open. A union of infinitely many open sets is still open. Intersection of infinitely many open sets, not open. Well, it could be, it doesn't have to be. Typically, it won't be. But as far as finitely many open sets, yeah, you can do that. If you take the intersection of finitely many open sets, it stays open. But you really only have to show it for 2 sets, because once you show it for 2, then you can take the intersection of the first 2, and then intersect with the third, intersect it with the fourth, so on and so forth, like that. Eventually, you get to the intersection of all of them. Okay. Sequences. So yeah. So we say, given a metric space M, when we say that xn is a sequence in M, we mean that xn is, the following list. X1, typically starting at 1 or starting at 0, x2, x3, x4, dot, 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 of elements of M. So you call it xn. Okay? So now the definition of convergence. I mean, you talked about sequences back in Calc 2, right? Talked about sequences, talked about convergent sequences, and you talked about limits, right? Limits is a slightly more sophisticated, well, not slightly, but it's a more sophisticated notion of the idea of a sequence. And you talked about limits of sequences and limits of, limits of functions in general. And then you talked about convergence, but you never really give a real definition of convergence, because the real definition of convergence is, or maybe your teacher did. I mean, we, for decades now, I don't know, maybe over 100 years, we've been sort of pretending to say, yeah, we cover the definition of convergence in calculus, but we don't. Nobody ever did. It was never covered, and it was never learned, not by, except by a few students. I mean, it's tricky. It takes some time to think about it, and there's other things that are more important to learn in calculus, like how to apply calculus, than really learning about limits. But you got to do it at some point. So in a metric space M, you have to do it at some point, but not everyone has to learn it. We say that sequence xn converges to L. And you write this as follows. Like that. When for any real number r, r bigger than 0, there is capital N such that for every m bigger than or equal to n, the distance from xm to L is less than r. So this is a for every there exists, for all there exists type statement from predicate logic. For all there exists. For any real number r, there is a number n such that for every little m bigger than capital N, the distance from xm to L is less than r. So here xm is just one thing in the sequence. So we use xn to mean the whole sequence, and then this xm means a single number in the sequence. Not a single number, is a single element. Right, so sometimes when you write xn, you mean the whole sequence. Sometimes you mean just a specific element in the sequence. Here we mean the specific element in the sequence. So intuitively, here's the intuitive picture. In R cross R. So here's L. And here's the ball of radius R around L. The sequence x1, x2, x3, x4, x5, x6, x7. So 1, 2. Eventually, you go inside the ball and you stay there. Eventually, the sequence goes inside the ball and stays inside the ball, no matter how tiny that ball is. No matter how tiny that ball is around L, maybe we should make that a different color. No matter how tiny that ball is around L, eventually the sequence goes into that ball and stays inside that ball. That's when you have convergence. If you don't have convergence, you know, there's some balls that you know, are too small. You never get stuck inside there. Okay. When xn does not converge to L, there is some r such that xn never stays inside BRL. Such that xn, like, you know, always it could keep going inside there, but it keeps coming out. Not never stays, so it doesn't get stuck in L, I guess. Doesn't enter and stay inside L, or BRL. So, for example, so in metric space R, consider the sequence minus 1 to the n, right? In other words, this is a sequence minus 1, 1, minus 1, 1, minus 1, 1, minus 1, 1, so on and so forth. This sequence does not converge. Converge to any L in R. Right? Doesn't converge to any L in R, in particular not L equal to 0 or 1. Or not 0, negative 1 or 1. Right? X minus 1 to the n does not converge to 1 because which ball around n does the sequence fail to get stuck inside of? Which ball around, not n, which ball around L, which is 1 here, does this sequence fail to get stuck inside of?
I mean, every other option would go to negative 1 does not then set the ball of 1.
Yeah, because the ball around 1, right, here's the ball of radius a half around 1. So here's 1, and then here's 1/2, and here's 3/2, right? So that's the ball of radius 1/2 around 1. So here's 1, and here's negative 1. Right, so the sequence, it keeps hopping back and forth. It goes in the ball, goes out, goes in, goes out, goes in, goes out, goes in, goes out. In other words, it never gets stuck inside there. There's a subsequence which gets stuck inside there, and that's fine. Right? Sorry, does not converge, not does converge, does not converge. There's a subsequence that gets stuck inside there, and that's fine. But the whole sequence doesn't. Okay, so it doesn't converge. Same thing for any other number L. It's just, you know, any ball around L is just not, you know, it's not getting stuck in there. How about an example of a sequence that does converge? The sequence 1 over n, well, let's say 1 over 10 to the n does converge to 0. Let's prove that. Let us prove that 1 over 10 to the n does converge to 0. Right? So you have to prove it how? For which r's? For which r do I have to prove that the sequence gets stuck inside that ball? For which values of r?
Any value of r?
Any value of r. In particular, r that's so minuscule, so tiny, it's smaller than the length of the Planck constant or whatever. In particular, you think of r as something really, 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 really small. Okay, so somehow it's got to get stuck inside there. Right, so let r be bigger than 0. Let r be bigger than 0. Right, in the decimal expansion, of r, right, there is a first digit. Right, there is a first digit that is non-zero. Right, that is, right, r is equal to 0 point digit 1, digit 2, digit 3, digit 4, blah, 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 so on and so forth. Right, say that digit 1 is equal to digit 2 is equal to all the way up to digit n minus 1 are all 0, but digit n is not equal to 0. So so r is 0.000000000 something something 0005, right? So eventually you get to some digit that's not 0, say the nth one. Okay, so now for any m bigger than or equal to n plus 1, right, 1 over 10 to the m, right, is less than r. So that means that right, so that's the distance to 0. So 1 over 10 to the m minus 0 is less than r, and that's equal to the distance of 1 over 10 to the m and 0 as required. Right, because 1 over 10 to the m, that's 0.00000001, where that first 1 is in the digit n plus 1. Right, is in the n plus first digit. Right, 10 to the minus 1, that's 0.1. 10 to the minus 2 is 0.01. 10 to the minus 3 is 0.001. So 10 to the minus m is 0.00000, and then a 1 somewhere past the n plus first digit, which is going to be less than r, because r is 0 at the nth digit. And that's how the ordering of the real numbers works. Okay, so that's all for today. So sequences, they're really important. So we're going to be, talking more about those, and I'll give you maybe a few sample problems for the final exam on sequences, to do, to think about. All right? Okay.